Hey there, calc folks. Back here with another video in our, our introduction to the concept of a limit. And we're at the point in our study where we need to start to examine what's called the precise definition of a limit, right? We need to go a little further into the theory and actually go about precisely defining what it means to be a limit, right? And get into some of the parts that we haven't defined as precise as we can, right? As accurately as we can. So we're going to jump into that today in a few of the videos I have prepared for you. I'm going to do this bit by bit. I think that's probably the better way to do it. I'm going to introduce you to the generic definition for a few of the cases, or for all the cases that we've talked about. And I have an example for each. And I will present those in pieces here, folks, is how I'm going to look at doing this. Okay, just so that it's not so overwhelming in an hour-long video. All right, let me bring up the precise definition here. Well, let's bring up the notes, and we'll get into the precise definition. This is not the precise definition, folks. This is just where it all begins, right? Again, if we go back to what we understand for a limit, right? When we have a functional relationship, y equals f of x, right? And we mention or we're interested in the limit as x approaches a for f of x, and we say that that is all equal to L in a mathematical statement, right? What that means, right, is that f of x approaches L, right? The dependent value of the function f of x approaches that value of L, right, along the dependent axis, as x, the independent value in the function, approaches the value of a, right? The value of a found along the independent variable axis, right? Now, we could say this with some other words, right? How you'll sometimes also hear this said is that f of x becomes arbitrarily close to the value of L as x becomes significantly close to the value of a, or sometimes we'll say sufficiently close to the value of a. All right? This statement, the limit as x approaches a for f of x equaling L, we've kind of had this understanding, right? That basically f of x gets close to L as x gets close to a in value, right? Or as f of x becomes arbitrarily close to L in value as x becomes sufficiently close to a in value. Right? This has been our generic understanding, right? But it does lack a little bit of precision. If we were to think about this second statement, what does it mean to become arbitrarily close to something? Or likewise, what does it mean to become significantly close to something? Or sufficiently close to something? All meaning relatively the same concept, right? Well, that's where our definition lacks a little bit of precision. There is a way that we can consider those meanings, right, with a little bit more of a mathematical context. And that's what we see used in the precise definition of the limit, right? To provide a little bit of mathematical meaning to these terms, what we do is we give some variable value to what it means to be arbitrary or significantly close. What we do is we set up a distance, a boundary, a distance to a boundary, where if we're within those bounds, we are what we consider arbitrarily close or significantly close or sufficiently close to some value. Right? And in these terms, what we use, right, in the case of a limit, is we use the values we call epsilon and delta. Right? We let epsilon be a distance that is considered arbitrarily close, and we let delta represent a distance that is considered significantly close. Basically meaning the same thing, right? But specific to this arrangement in the statement, right? Using epsilon and delta, right, we can present what's called the epsilon delta definition for a limit, right? Epsilon and delta, again, being this size of boundary that we can put around the values we encounter in our limit that allow us to say that we are arbitrarily and significantly close to these values. Let's look at the definition. This is the epsilon delta definition of a limit. Right? I think I probably said this in class. And it's begun to become ingrained in me, right? But it is a way of saying that for any, for y equals f of x, right? The limit as x approaches a for f of x equals L means for every epsilon greater than 0, there exists a corresponding value of delta greater than 0 such that the absolute difference between f of x and L is less than epsilon whenever the absolute difference between x and a is less than delta. It's called the epsilon delta definition of a limit. And I just read it pretty much verbatim to what you see here. This is why we didn't start day one with this material, folks, right? This is why day one we start with a very loose definition of what it means to be a limit. We start back with a definition where we use terms like arbitrarily and significantly close. Right? Because we don't need to necessarily get into this detail when evaluating limits. None of this detail was necessary to go about with some sort of strategy or procedure, some technique that we developed for evaluating a limit. All this definition is primarily used for is a means of proving our solution as being correct. Proving that what we say here is the answer for L is indeed the value that f of x is approaching when x, the independent variable in that functional relationship, is approaching the value of a. Right? This, what we call epsilon delta definition of a limit, is just a means of proving the result of a limit and not so much used in actually finding the value. Right? If you notice, this definition really does imply that we already know what L is, right? To be able to define this limiting statement. Right? So, to interpret, again, what we've said about epsilon and delta is that they are a specific size of boundary that we place around the values in our limit. Epsilon is going to be a size of boundary that we place around our value of L inside of our limit. This is a boundary that's actually placed around the value of L. Right? What we say is the value of our limit. What we say is the value that we're trying to get what? Arbitrarily close to. Right? To be arbitrarily close is to be within epsilon units of L. And regardless of that boundary size, what this definition says is, if this statement is true, you'll always be able to find a corresponding size delta. What does that mean? There'll always be able to find a size delta, where when we think about delta could be thought of as being a function of epsilon, or being dependent on epsilon in a sense. Right? We say that there exists a corresponding value of delta. Right? A delta that's related to epsilon in some sort of correspondence. That's also bigger than 0, right? Where again, it's a size of boundary. It's a size of boundary here that we place around this value of a, the value that we're approaching. It's a size of boundary that stands for being, again, significantly close to that value of a. If we're significantly close to a, we are within that boundary. And what this definition says is that to be arbitrarily close to L is to be within this boundary, or to be what we would say is an absolute difference between the output of the function f and L being smaller than that boundary size, whenever it is the case that our independent value x and a, their absolute difference, right, does exist. It's greater than 0, but it's smaller than a boundary that corresponds to epsilon. That this statement always implies this is going to occur, no matter what size epsilon there exists and that we happen to be given. Right? Delta will always exist that will be corresponding to epsilon, such that when we think about the absolute difference between these values x and a will be less than that delta. Being less than that delta would imply that the absolute difference between the output of the function f at that x and our limit's value would be less than that epsilon. A little bit of theory there. Now, let me put that theory into picture. Here's an illustration of that theory. That's right. The following here, we're not going to be able to see both in the same picture, but I can get this in there. Here's an illustration of what's going on, and there's a lot of dashed lines here, so bear with me. Right? But I do try to explain above. I say the following illustration here of the epsilon delta definition of a limit for a linear function, right, is given. Notice, for every choice of x sub 1 in this illustration, now where is x sub 1? Here is one choice for x sub 1 I'm illustrating down here. But no matter, for any choice of x sub 1 in this interval, right, for every choice of x sub 1 in the interval a minus delta, a plus delta, delta being the size of boundary that we're placing around the value of a, right? It's going to create this interval around a. And no matter what size x I pick, x1 in that interval, the corresponding value for the dependent variable, the value for the output of the function at that x, f at x sub 1, seen over here, right, along the vertical axis, its value will always lie within this interval. This interval that forms around L, and that is the size of epsilon. Epsilon units above L and epsilon units below L. And what the epsilon delta definition says is that f of x sub 1 is considered to be arbitrarily close to L if it lies within this interval, whenever x sub 1 is considered to be significantly or sufficiently close to A to lie somewhere within this interval. And we say that by saying that no matter what size epsilon you choose, this interval can be any size. Notice this illustration has no scale along the vertical or horizontal axis. This epsilon can be of any size, right? There will always correspond, and that's what these horizontal to vertical dashed lines are indicating at these boundaries, is that in this case of this linear function, they'll always correspond a delta, right? From this size boundary, you can always go over and measure a corresponding value, a delta on the right, or a boundary on the right that corresponds to a size of delta. And from this boundary on the left, or from below on L, you'll be able to go over and indicate that, yeah, they'll always correspond this corresponding boundary on the left of A. Such that whenever you pick a number in here for x, you'll always be really, really close to this location on our graph, which means the output of your function will always be within this boundary of epsilon. For every epsilon greater than 0, there is a corresponding value, a delta greater than 0, such that the output of our function f at x sub 1 is within these boundaries whenever the absolute difference between x sub 1 and a is within these boundaries. That is the true meaning of the limit as x approaches a for f of x equaling L. No matter what size epsilon I have here, I'll be able to find a delta that's based upon that epsilon. It will be determined in how it corresponds by the behavior of our function, but it will exist such that if you pick an x in this interval formed by delta around A, you will find an f at that x that's within the interval of size epsilon around L. That is the epsilon delta definition of a limit. And again, that is how we interpret this value, the limit as x approaches a for f of x equals L, where, again, here we're saying a and L are real numbers, right? That is one thing we have to take away from this definition. This is for that specific case, all right? Now, we can use this understanding, as I had noted, to prove a limit. We're going to start with a real simple proof, the proof of a linear function, right? Here we might consider proving the limit as x approaches 3 for f of x minus 8 is equal to the value of 7, right? And we can get there through substitution. We know by technique we don't need the epsilon delta definition to evaluate this. It is just 5 times 3, which is 15, minus the 8 equals the value of 7. We can find that result using substitution rule. But why is that true? Why can we safely say the value 5x minus 8 becomes arbitrarily close to 7 as this value of x becomes sufficiently close or significantly close to this value of 3? Well, that's because the epsilon delta definition of the limit holds true. That for any size epsilon greater than 0, I can find a corresponding size delta greater than 0, a delta based upon that epsilon, such that when I pick an x sub 1 in this interval formed by delta around A, I can find f at the value of x sub 1 in this sized interval, epsilon-sized interval formed around the value of L. That is why I can safely say this, and I can show that through proof, right? Here's how the proof begins. Every proof of the epsilon delta definition has some preliminary work. And I'm going to warn you, the preliminary work is going to look like the proof. We're going to get done with the preliminary work, and you're going to go, okay, we proved it. And I'm going to go, okay, but we have to be careful. The epsilon delta definition says, right, if we go back to it, that for every epsilon greater than 0, there exists a corresponding delta greater than 0, such that this occurs when this occurs. Kind of implying in order that this is going to have to happen. Well, this is going to have to be the setup that implies this is the result, right, of that setup. Well, our preliminary work is not structured in that manner, right? If we notice from the epsilon delta definition of a limit, for every epsilon greater than 0, there must exist then a corresponding value of delta greater than 0, such that what we would be able to say is that the absolute difference between f of x, which would be 5x minus 8, and the output of our limit L, the value is 7, must be less than epsilon whenever, right? Whenever the absolute difference between x and a, the value seen here in the limit statement, right? When their absolute difference is less than delta, right? This is what we need to show, is that for every epsilon greater than 0, I can find a delta based upon that epsilon, such that when I set up this statement here, I can show it implies this statement here. All right. Now to get there, I do some preliminary work. Right? To illustrate the proof, where I begin is with that implied statement. I start with the end of where I want to finish. And I note that if I do a little simplification there to the absolute value argument, I end up with the absolute value of 5x minus 15, right? Drop the parentheses, negative 8 minus 7, right? Drop the parentheses, negative 8 minus 7 is negative 15. That argument simplifies to 5x minus 15. Where you might notice inside 5x minus 15, you do have a constant multiple of 5. And you could factor that out of both terms, 5x and 15, and that'll leave the group x minus 3 times 5. Now notice that x minus 3 is the x minus 3 seen up here in the delta statement. We're following with some properties of absolute values. Absolute value symbols will distribute themselves across products. They're a lot like a radical in that sense. So I can think of this as the absolute value of 5, right, times x minus 3, or what is in turn just 5 times x minus 3, where I can divide both sides by this value of 5, and I can end up showing that the absolute value of x minus 3 must be less than epsilon divided by 5. Where what you can note is this statement seen up here, and what I'm trying to initialize in my proof, right? Where the delta now is being expressed in the terms of epsilon, right? If I think about it, I might make this connection, right? That delta could be thought of as being epsilon divided by 5 in my proof to allow me to show that this will always imply this. And I have that proof, right, all worked out with this preliminary work done in my limit. Well, in my proof for the limit. All right. So I'm going to make that connection here. This result implies letting delta equal epsilon divided by 5. There's always going to exist a, and I should maybe say a corresponding value of delta greater than 0, right? For every epsilon greater than 0, right? If I choose an epsilon of 25, I know I'm going to pick a delta of 25 divided by 5. If I pick an epsilon of 1/5, I know I'm going to pick a delta of 1/5 divided by 5, which is 1/25. right? I know for every epsilon that I'm given greater than 0, my delta chosen, right, that also is greater than 0 is going to be that epsilon divided by 5. And that this statement here, where I can say epsilon, or the absolute value of x minus 3 is less than delta, which is equal to epsilon divided by 5, will end up implying then that the absolute value of 5x minus 8 minus 7 will always be less than epsilon, right? And it will imply that, right, if I work through that implication, and that's what I probably should say here, implies that if I bring that 5 back over as an absolute value, which you can do because 5 is technically the absolute value of 5, I'd be able to write this statement here, right, which further implies that I can bring that 5 in as a constant multiple, and say this statement here, where then that can be written, as we have seen, as this statement seen here, right? Where I know that then can be expressed as this final statement seen here, right? All of these implications come about, right, from the fact that I can let delta equal epsilon divided by 5. Right? I've shown that for any epsilon there exists a corresponding value of delta greater than 0, epsilon divided by 5, such that if I start with this statement here and let delta equal epsilon divided by 5, I can work backwards through that statement, or I can work backwards through my preliminary work. I can take this statement seen here and transform it through this algebraic work that I've worked out through the preliminary work into the result I need to prove the limit. That the absolute difference between f of x and L is less than epsilon. That is my proof. All right? That's the epsilon delta definition, folks. We're going to work through a couple more examples in class. And I have a few more examples to give here on video. It is that convoluted, yes, at times. It is that heavy in theory, yes, at times. Is it necessary to evaluate a limit? No, it was never necessary to evaluate a limit. That's kind of what we should take away from this. But if we want to call ourselves students of calculus, right, and we all want to, at the end of this course, call ourselves students of calculus, right, we do want to make an attempt to understand the epsilon delta definition of the limit. We do want to appreciate the epsilon delta definition of the limit. We do want to attempt to be successful with some proofs of the epsilon delta definition of a limit. Right. The proofs do get a little trickier when you move out of the case of a linear function. The choice for epsilon isn't going to be always so clear-cut. But again, it's going to be some heavy theory that we're going to use to still be able to prove that for every epsilon greater than 0, there exists a corresponding value at delta greater than 0, such that the absolute difference between f of x and L is less than epsilon whenever the absolute difference between x and a is less than delta, when we make the statement the limit as x approaches a for f of x equals L. The epsilon delta definition. All right. So I do have another video for you here where we're going to look at a little bit more of that complexity. We're going to go from a linear case up to a quadratic function and consider the limit there. All right. and begin to appreciate these two cases. And typically that is enough in our study to walk away with the epsilon delta definition and have some experience with it. So that is what we're going to do, folks. So I will have that video out for you shortly, and I'll end this video here. I'll see you next time.